Okay, welcome to this video for Chem 161, some Chapter 2 content, where we'll talk about the mole and Avogadro's number, Na. We'd previously seen in the course and in a separate video that we can refer to the mass of a single atom by atomic mass units. And so typically we count the number of protons and the number of neutrons. And so for one atom of carbon, we know that the mass here is going to be 6 protons plus 6 neutrons. And so this is going to give us 12 AMU for the carbon-12 isotope. And again, this is just one atom. Invariably, when we work with matter in the lab, we like to work with masses that we can typically see and handle and kind of manipulate in beakers and using other kind of macroscopic tools. Handling one atom of carbon is very challenging, and few scientists get to do that. So to handle more like an amount of carbon, which is the main constituent in, say, a lump of coal, and a lump of coal might be on the order of 10 to 12 grams, we might want to know how many atoms of carbon are in that lump of coal that's on the order of 10 to 12 grams. And so it turns out that when we do lab work like this, that we're typically working with on the order of 10 to the power 21 to 10 to the power 26 atoms when we work with masses of carbon that are on the order of 10 grams, like a lump of coal. And so to kind of give us a better idea about how many atoms exist and to kind of get the information from the periodic table away from this atomic mass unit, but something more in line with the masses that we're used to, like grams, like a sugar cube being roughly 1 gram of material, we need a unit to help us with that. And so we have the mole that helps us there. Okay, so we'll learn that 1 mole here is defined as an SI unit for expressing quantities of substance. Okay. And so 1 mole of substance is defined as the quantity of it that contains exactly a huge number, as we'll see, of elementary entities. And those could be atoms, ions, or molecules. Okay, so 1 mole, let's write this out, is the quantity of a substance that contains exactly, and here's where our big number comes in, 6.022140076 times 10 to the 23 entities. And to put a better word for entities, if we're talking about materials like chemicals, we'd be talking about atoms or ions or molecules, ionic compounds, etc. Okay, so in chemistry, we typically refer to amounts of materials by mole, which means we're talking about 6.022 times 10 to the 23 molecules of material. Okay, so 6.022 times 10 to the 23 molecules of water is just under a tablespoon of water. Okay, so again, that's an amount we could use in the lab quite easily and routinely. Okay, so to frame this using language that you may have seen elsewhere, you know the definition of a dozen. A dozen is the quantity of substance that contains exactly 12 entities. Okay, so if we're talking eggs, 1 dozen eggs is 12 eggs. Okay, 1 mole is the quantity of a substance that has this huge number of entities, and that would be atoms or molecules or compounds. Okay, so your textbook gives you this number with all these digits. We'll be responsible for knowing and memorizing this number. Okay, so I'm going to put a big asterisk here. We need to know that 1 mole equals 6.022. We're going to memorize this number to 4 significant figures times 10 to the 23 units of that substance. Okay, so I'm going to kind of put a blank here where we need to know more. If we were talking about atomic mass, then we would have, under that squiggle, we would have 6.022 times 10 to the 23 atoms is 1 mole of that atomic, that material, that elemental form of material. Okay. Good. So, and again, you can think about approaching questions using the mole, thinking about 1 dozen. So often a good thought process is try to think about the question, replacing words like mole with dozen, and see if you can understand that. So again, 1 dozen would be 12 something. So a dozen eggs is 12 eggs. Okay. All right. So with that, we are now allowed to think more about what this means, knowing the identity of the mole. By the way, this number is very large, 10 to the power 23. Your textbook has a good kind of way to calibrate us to the size of this number. One topic that they say is that there's about 3.7 trillion cells in a human body. And if we wanted to know the number of cells on Earth, that if you total up all the cells from all the people on Earth, that is about 8 billion people, we only have half a mole of cells. Okay, so we're only halfway to the full mole if we count all the cells on planet Earth due to humans. It's a huge number. Okay, so with that, we can talk about things like molar mass now. So molar mass is going to be defined as the mass of 1 mole of an element or compound, etc. Okay, so often this is given capital M subscript M or capital M subscript W for molecular weight. But for now, let's work with capital M subscript M for molar mass. Okay. So rewinding to what we said about carbon, 1 atom of carbon 12, we knew that to be 12 AMU. This allows us now to say that 1 mole of carbon 12 weighs exactly 12 grams. Okay, so in other words, the molar mass, or the atomic mass, better said, because we're talking about atoms here, the atomic mass for carbon is 12 grams per mole. Okay, so let's see there. If we ask the question, what is the molar mass of carbon we could turn to the periodic table and we would see that we have listed 12.01 as previously thought as AMU. We can now say that this is grams per single mole of carbon, okay? Now notice that this is a little bit different than what we have up here in that we have decimal points 01, and that comes from the concept of isotopes. Recall that we have about 1.1% of carbon-13, which adds an extra neutron to every nucleus, and there's a little bit of carbon-14 as well. And so our average mass for all carbon is going to be heavier than 12 exactly. And we see that in the decimal points. Okay. All right, so this is sort of more simple, or simplified down to say that the molar mass for carbon is 12.0 grams per mole. Okay, and that's how we would use that number. Okay, so looking at this number again, 1 mole of carbon weighs 12.01 grams because I have a mixture of isotopes there. Okay. So what else can we do with this? Well, we've just counted, the mass of 6.022 times 10 to the 23 carbon atoms is 12.01 grams. What about something else? What about 6.022 times 10 to the 23 molecules of water? How much does that weigh? So the weight of this so we start using the information from the periodic table. We see that hydrogen is listed as 1.0079 grams per mole. So if I had 6.022 times 10 to the 23 atoms of hydrogen, that would weigh 1.0079 grams. Also on the periodic table, we see oxygen, and this is listed as 15.999 grams per mole. So if I had 6.022 times 10 to the 23 atoms of oxygen, that would weigh 15.999 grams. Now, from the formula, we know that there are 2 hydrogens and 1 oxygen per molecule. So we have to do a bit of a sum here. We can take 2 times the atomic weight for hydrogen, 1.0079 grams per mole. That allows me to have counted all of the hydrogen in 1 mole of this compound. 6.022 times 10 to the 23 molecules of water has 2 times 6.022 times 10 to the 23 molecules of atoms of hydrogen. Okay, so this is the hydrogen piece so far. And I'm going to add that to 1 times 15.999 grams per mole for the oxygen. And so the sum here gives me the weight of 1 mole of water molecules. Okay, so this will be punching this out on your calculator. 2 times 1.0079, 2.0158 plus 15.999 tells me that this is 18.0148 grams per mole. Okay, so rewinding here, 6.022 times 10 to the 23 molecules of H2O weighs 18.0148 grams. Okay, and so hopefully that sentence helps you rationalize the per mole 18.0148 grams per mole of water. Good. Okay, we'll do one more quick question. So how about how many moles of sodium Na are in a certain mass amount, are in 95.3 grams of sodium. Okay, so that's our question. So what we want to try to do is go from mass information to moles. Okay. So to handle this question, we start with the mass information. 95.3 grams was the sample amount. And we want to try to transform this into moles. Okay. So when we turn to the periodic table, we see that sodium is listed as 22.98 grams per mole from the periodic table, so sodium, okay? So we should be able to go from grams to mole by using a conversion factor based on this. Okay, so if we invert this number, we can put the mole as the numerator, so we'll create a conversion factor. 1 mole of sodium weighs 22.98 grams. And if we have 95.3 grams, clearly we have more than 1 mole. Okay, so this conversion factor will convert us from mass into moles. Okay, and so this would take us through to the answer, and this is going to be roughly 4.15 moles of sodium for our answer. Okay,